So hi everyone, welcome. Have you ever wondered that where to start UPSC CSC physics, or what could be your source, or how many different sources do you even need truly? And then the next big thing, that how to solve PYQ, or the consistent wondering that should I make short notes or continue with PYQ, or we should make both. And if you are doing this much in the physics, then would it be tough to manage GS with physics? These all questions will be answered in this introductory series of full-fledged course UPS of 2026, which is a complete success blueprint for UPSC CSC physics. So everyone, welcome. Today we are diving deep into exciting world of physics for the UPSC CSC. You might be wondering, where do I even start, or how do I tackle all those problems which we just discussed here. Don't worry, we have got you covered with this full-fledged course of 2026, which is aimed at UPSC CSC 2026, and in short we are calling it FFC 2026. So in this course we will explore different resources at a single place. We will solve problems together along with the predefined categories of introduction, solution and conclusion, so that you can get the complete 360-degree spatial overview of the questions which we are going to solve, along with the uh, PDF solution. And you will even learn how to make killer short notes, so that on your mains examination day you really make it well. Then next we will also try to balance and manage the preparation of GS with physics. So this whole introductory series is about the short introduction of these all questions which we are going to uh, start. So let us know something, that there are some hard facts, that less than 10% or about 10 to 12% of the physics optional candidates score 250 plus marks, and this is about like those who are doing really good. Okay, so this is the rough estimate. Okay, and there are many people who are struggling with paper 2 numericals, because we all know that paper 1 numerical is broadly class 12 level numerical. Okay, broadly, not exactly. So you have got the concepts from class 12 or IIT JEE preparation, so it might work there. And we also have a lot of Indian sources for paper 1, but for paper 2 we do have the good balance in between concept and numerical question. Okay, also, because UPSC syllabus is overwhelming, and you will have your GS preparation, okay, broadly in two format. One is prelims, another is main examination. Then you have within the main examination, you have broadly three. One is GS itself, one is GS itself, another one is your physics optional, and the third one is essay. Okay, and within this GS, the most important one for us is ethics paper. So broadly, I will try to boil it down, that people find it tough to balance in between physics, ethics paper, and three essay paper. Okay, so to balance this all, you must make this physics as productive and efficient as possible. Okay, so also we have limited quality resources for UPSC specific preparation, and we often wonder whether to follow foreign author books or Indian author books. Foreign or Indian, and if both, then which book and what topics exactly, because we cannot cover all topics from each and every book. That will uh, waste a lot of time. So in this all we have three pillar success framework. Okay, the first one is conceptual mastery, because if you study concept really well, then only you can apply it. Then only you can apply it, and apply means solving the numerical program. or where some kind of analytical or interpretation skill is required. Analytical or interpretation is required. Okay, so this is where we need the conceptual mastery. The next one is once you do the conceptual mastery, you need to solve the problems roughly. Like at first, they will ask you the basic question to establish two body collision in laboratory frame and in center of mass frame. So at first, your approach will be state to directly do it objectively. Do it objectively, like not writing much of the subjective words, not writing much of the physics language, like we do really do in 10 marker, 15 marker question. You just think that you are trying to solve it objectively, like you do in the IIT JAM examination or IIT JEE examination during your class 11th and 12th preparation. And when just you master this all UPSC pattern numerical examples, you become some kind of expert, not exactly 100%, but might be some kind of, because why not hope positive. So then at final we arrive at the answer writing, where you have chunks of learning from, like you have concept, CI, and then you have the associated learning of numerical NI, then you make the complete answer out of those. So this will be the third step. Okay, so this is the three pillar success framework. It is very easy. Once you will watch the introductory lecture as well, after this introductory explanation, then you will know that what I was talking about, why the conceptual mastery. Because conceptual mastery is the single most important thing that will help you to solve the numerical and analytical question. So what you will get um, and I'm not sure about this 200 plus, because I am really trying to squeeze it out. Okay, so our job will be less hours. Okay, by using the PDF. Okay, and mentorship, because we cannot afford to waste time. The reason is very simple: we need to prioritize GS, and we will cover both paper 1 and paper 2. Okay, we will have the interactive doubt solving sessions. Okay, and our notes will be concise and exam focused notes. Okay, we will have the ideas of the formula sheets and quick revision cards, but this will be handmade by you. Okay, and sometime we will have current affair integration, like if there is some kind of a special development at some great places like CERN, or some kind of news about fusion. Okay, or any kind of news, we will cover that as well. Then there is practice and assessment, where we will have the topic wise test series. Okay, where I will give you questions and you will solve them, and then one day after I will give you solution. Okay, we will have the PYQ analysis with solution of minimum from 2011 to 2025. This is what we are going to have minimum. Okay, and we will have weekly answer writing practice of 5 to 10 questions. Okay, so there will be no dearth of you. And what in the answer writing practice will try to solve PYQ and similar questions to PYQ again and again, so that there is conceptual mastery. Okay, and I will try to help you in the personal study plan creation, because some of you might be good in GS, some of you might be beginners, so you need to focus on GS as well. Okay, and we will have the one-to-one guidance session as well, and I will also help you to write journal, because journaling is very important for the self discipline, for the self discipline. Okay, and this will help you to become a consistent person, the man of focus, the man of, or the person of focus, the person of determination, the person of high confidence. So we have limited seats available, and this is my contact surface. So you just can message me on Telegram at this user ID, or this is my email ID, or this is the website which we update regularly with different study sources. Okay, so success is where preparation meets opportunity, and this is what I'm trying to define with this course. And let me make one thing even more clear from where we started, that these are the five fundamental questions. The first question is where to start. The answer is start with the mathematical mastery, because we cannot study physics without mastering the mathematics. So there are certain tools, certain mathematical concept like vector integration, okay, or broadly calculus, okay, Dell operators, Laplacian, a different type of coordinate system like Cartesian coordinate, polar coordinate, cylindrical, spherical, okay, Taylor expansion series, and these all. So it is exactly how our program is designed. So this is what I'm answering, that where to start. The answer is you need to follow the lectures. The lectures are prepared in the way that you need not to think about where to start. You just need to execute whatever the program is trying to dictate to you, and rest time you will dedicate not in thinking but actually executing your GS plan, because you need not need also to prepare for prelims and mains. Okay, how many different sources? Again, we have covered this for you. So sometime like thermal physics is very simple. Thermal physics is simplest. You just need a book of thermal physics by Garg, Bansal and Ghosh. Then some are very complex, like for example uh, electrodynamics might be, why not, mechanics itself. You have normal mechanics like which we all have studied. Then we have a specific mechanics like a special theory of relativity, or rigid body dynamics, or like fluid dynamics. So there is a mix of a straightforwardness and complexity both in the UPSC CSC physics syllabus. So we just understood that where to start and what is the source. Source will be given to you, okay, in the form of video lectures and notes. How many different sources? We will see it ourselves. Okay, we will combine all this. Okay, and this is already being done. If you have noticed, there is another program we have which is called intensive support program, ISP, which is purely mentorship program. So here we have already demonstrated and it is being loved by the people. Okay, how to solve PYQ? You will get solved PYQ PDF. You will get solved PYQ PDF. So again, no worries about this. This is also covered for you. And the next part is, would it be tough to manage GS with physics? The answer is yes, it is tough, but you can minimize the toughness. Minimize by following the simplest strategy, that is concept plus solve similar question to PYQ plus PYQ. If you do this, you are done. And the most important part, which is which I think is making killer notes. Making killer notes which are very short. So we are required to make killer short notes, because if some of you have written the mains examination, you will know that revision is very important in those last moment. Revision is god. Without revision you will perform at least 20% bad. Okay, so last week revision and last day revision is very important. So this is what we all are going to do in this well designed full-fledged course of 2026, and syllabus completion time will be January 2026, so that you get ample time. And let me tell you very clearly that this a whole series is devised in a way that you will get at least 4 hours per day for GS as well. So your basic timeline will be to study physics 4 to 5 hours per day, and if I tell you, so it will be around 4 days in a week. So you will have a lot of spare time for GS as well. Okay, so this is what I wanted to say, that this is the first time that we have already used each and every book in the market to analyze that which is the best book, and this is the way we have devised the full-fledged course of 2026 specifically meant for the UPSC CSC physics optional. So I hope you will love it, and this will be really effective for you if you follow just one simple step, that is execution of whatever the course is saying to you. Okay, and the most favorite quote which I would like to share with you is, just do it, don't think, just do it. This is what I would like to say to you. So execution is the key, and in the next part of this you will have one very detailed lecture which will be from the FFC 2026 course as a demonstration or demo video. Okay, so let us meet in the demo video. Thank you for watching this. So hello, welcome everyone. So today we are going to start the first lecture of quantum mechanics, and in this we are going to learn about the origin of the quantum mechanics. So in general, the origin of the quantum mechanics, we generally start with understanding the wave particle duality. Why? Because at first, when there was a development of quantum mechanics going on in 1900, so there was Planck hypothesis about the discrete nature of energy. So there was the concept of energy quantization first revealed during the development of understanding of the black body radiation. So what we will do, we will study two things. The first one is particle behavior of wave, and then wave behavior of particle. And this is completely known as wave particle duality. So our first lecture will be about particle behavior of wave. In this we are going to understand black body radiation, photoelectric effect and Compton effect. And let me tell you, there have been direct question from black body radiation and Compton effect as of now. So the first thing we are going to learn about is the origin of the quantum mechanics. So let us try to understand what is black body. So black body is any object which absorb all the thrown radiation on it. Okay, so there is some object. So whenever you throw some kind of radiation, obviously through the electromagnetic wave, then it will absorb each and every, and it will also emit all of them. You know, absorb and emit. So it will nothing will get absorbed in the material itself. Everything will be absorbed 100%, and 100% will be emitted as well. So why black body is important? The answer is, its study led to beginning of the conceptual fabrication of quantum mechanics. So while we were trying to understand the black body radiation, so we finally, because of the Planck, we introduced the discrete nature of energy. Okay, so that was the reason. So, but black body is the idealistic formulation. The ideal black body does not exist in real, but we could have the nearest approximation. So the nearest approximation in that case is a hollow enclosure which has a small entrance hole and blackened inner wall. So this particular thing is actually a black body. The nearest approximation, not the ideal one. It has one teeny entrance, obviously for radiation to come in. Once the radiation comes in, you will find the inner walls are blackened. So we know that black things absorb all the radiation or most of it, if not all. And this will cause this successive reflection inside the black body till each and every energy uh, is absorbed within the black body. So it will be absorption of all the radiation thrown on it, and similarly the state of this black body, the atoms inside the black body, the state will rise, it will get into excited state, and then it will come back as well by emitting all the radiation. That is why we are calling that it will absorb and it will emit all of the radiation thrown on it. So suppose we have this black body, then we are trying to mark that how does the spectrum is being emitted from the black body. So let us try to understand this particular graph. So in this graph, we have the axis made of the wavelength, which is lambda, and we have the y-axis, which is intensity as a parameter, lambda as a parameter. Okay, so intensity is a function of lambda. So what you are required to do, you are required that observe. You observe that okay, as the lambda is less, so intensity is rising, rising, rising. But at certain point, intensity is maximum, and even if you now increase the lambda, okay, so it will be the same. The maximum will be the same. So there is certain maximum value, okay, for some lambda m. So we are calling it this lambda m to be that is lambda maximum, and we call this a spectral distribution of radiation from the black body. So black body radiates emission in this form, okay, that is if lambda is less, okay, so intensity will rise. So sorry, lambda is more, because if lambda is more, then frequency would be less, okay. Lambda is inversely proportional to frequency, and we relate energy to frequency. We relate energy directly proportional to frequency, because you must remember this formula, that energy is equal to h times nu, where h is the Planck's constant and nu is the frequency. So the converse would be that E is equal to hc upon lambda. That is why if lambda is more, okay, then energy would be less. So if lambda is more, energy would be less. But as lambda is getting reduced, the energy will rise. But even if you reduce the energy more than that, the energy would again decrease, which should not be the reality. So people were surprised. Okay, so why this is happening? Okay, so to explain this surprise behavior, okay, because if you reduce the lambda or increase the frequency, then energy intensity should have uh, risen, okay, it should have rise, but that is not happening. So for this particular reason, many theorists actually tried to explain the emitted spectrum, which is given here in the figure 1. So that was the main crux, okay, that you need to apply this formula, and the behavior is anti of that formula. The maxima is in this region, and then it keeps decreasing. So that should not be the case as per the classical physics. So this is where this question is how we were forced to think that okay, there is something more than classical physics. Okay, so many theorists tried to explain this, and some prominent theories were Wien's law, Rayleigh-Jean's law, and Planck's radiation law. Okay, so we are going to understand Wien's law at first. Okay, so and let me tell you, this very topic you will understand learn in the thermal physics as well. Thermal physics as well. Okay, but in the quantum mechanics we do it in short, just to know okay, this was the starting point of the beginning of quantum mechanics, theoretical obviously the theoretical fabrication of the quantum mechanics. So in Wien's law, what they did, they used the thermodynamics, dimensional analysis, and scaling argument to establish the fact that okay, intensity is inversely proportional to fifth power of lambda, that is wavelength, and directly proportional to some exponential function which depends on the lambda itself, as written in this formula. Okay, so we can say that okay, intensity in general is a function of wavelength and temperature. So this law, when you plot this law, so you will find that okay, such law are fitting good for the observed curve, but they are failing at the longer wavelength. Okay, so what you will do if you increase the wavelength, so this curve will be broadly like this. Okay, this is curve as per the Wien's law. So you know that the even lambda is less, so this region is well fitted. Okay, when lambda is less, so this region is good fit, but in this region it is failing. So this was the drawback of the Wien's law. Okay, next, this drawback was tried to be um, addressed by the Rayleigh-Jeans law, but it also has its own drawback. And finally, we had Planck's radiation law that correctly explains all. So let us try to understand what Rayleigh-Jeans law said. So we know that Wien's law is based on dimensional analysis and scaling argument and the minimal theory from the thermodynamics. So it was a kind of semi-empirical formula. Okay, it was not derived from the known and well-established theory. So people were not much satisfied. Hence, next theory was given by Rayleigh and Jeans. These were based on classical electrodynamics and thermodynamics. Okay, so people were little bit more surprised and satisfied because there were some alternate treatment here. So they assumed that the radiating body, the body which is emitting the radiation by observing something, because you can only emit something if you have that energy yourself. So at first absorption will happen, then radiation will happen. So they assumed that radiating body is collection of large number of charged particles. Okay, so okay, it is logical because atoms do have the particles because they are particles. So this is the collection of large number of what kind of particle? Charged particle. So okay, if they are there, then how they are radiating something? So we need to know that what they are doing, because if you know what they are doing, if there is a large number of charged particles, so we will have better idea. So the answer is they are performing linear simple harmonic oscillation. What kind of simple harmonic oscillation? The oscillation in between energy levels. So this is energy level 1, this is energy level 2. So as they are gaining the energy, so they are moving to energy level 2, and while losing, because every atom or every particle wants to have the stability, so they will move back to their original state. So in this they will absorb the energy, and in this they will emit the energy. Okay, so this is what the 100% absorption and emission is going on as per the idealistic behavior of the black body radiation. Okay, so we can say that these oscillating charges do emit and absorb the electromagnetic radiation. Obviously this h nu is nothing but the energy, okay, which we will know later on. So we can say that okay, if there has to be the thermal equilibrium, like heat has to be same before and after, then everything which has to be absorbed, that must be emitted. Okay, if something if even the some percentage of the mm, radiation will be within the said enclosure of the black body, then the thermal equilibrium will not be established. So we know that okay, there is a condition of thermal equilibrium where energy density of radiation within the cavity will be equal to energy density of the atomic oscillator at the walls of the cavity. So we know that, look, this is very simple to understand. We know that this is the black body. Okay, this is the entrance for the radiation to come in. Okay, now there will be multiple successive reflections till each and every amount of energy is being absorbed. Okay, so we can say that okay, this energy is being exchanged in between atoms of wall and cavity, because this you see that this cavity also contains the radiation, so there will be some kind of energy there. So we can say that if there has to be thermal equilibrium, that temperature should not rise, it should be equal. Okay, so we can say that energy density of the radiation within the cavity is equal to energy density of the atomic oscillators at the walls of the cavity. This is the condition which we And because now we have this condition, we can move further mathematically, okay, by using some kind of a statistical law. So mathematically, we later discovered that, because we need not to find how we discovered, it is not going to be the pure thermodynamical class, it is quantum mechanics class. So we know that, okay, this is the result and how they derived it. So mathematically, it was discovered that number of such oscillators per unit volume is function of frequency, and this is slightly mistakenly I wrote it. This is not correct. So it is 8 pi mu square upon c cube, and we know that this nu is what? This is frequency of radiation, and c is nothing but speed of light. Okay, so this was the correct formula. Okay, so we know that within the unit volume, the number of such oscillators, like such oscillators, the atoms which are oscillating, which are moving up in their energy state and then coming down. So it is 8 pi nu square c cube. Okay, where nu is frequency, as I just told you, and for such setup, the average energy given by the classical equipartition theorem is kT. Okay, so like there would be some kind of average energy. So classical equipartition theorem says that uh, the kT would be the average energy. So now you know the number of particles. Now you know the average energy per particle. So when you multiply them, you can get the energy density. When you multiply both of them, you can get the energy density. So this is the energy density. Okay, when this is the number of particles and this is the number of particles, or specifically oscillators, because they are doing oscillators per unit volume, per unit volume. And this kT is average energy. This kT is average energy. So when you multiply them, you will get the energy density. Okay, and again, and let me tell you, this is little bit wrong. This is nu and this is c. Okay, I have mistakenly written it in reverse. Okay, so okay, so this particular formula, we call it Rayleigh-Jean's law, and it is U is energy density. It is function of frequency and temperature, which is equal to 8 pi nu square upon c cube multiplied by kT. Now you know all the framework. How did we arrive at this, and why we are calling it energy density? Because this number is nothing but the number within the unit volume. So that is why we are calling it density. But again, the Wien's law felt at longer wavelength and this felt at shorter wavelength. So when you plot this, you will find that, okay, the plot is in this way. This plot is in this way, and this is Rayleigh-Jean's law. So you know that the curve is not getting fit properly by both of the laws. So that is why there is still some gap. Okay, and you know that if energy density is function of frequency, okay, this is the 8 pi mu square upon c cube times kT. Okay, so if this is the function of energy frequency, then as frequency is equal to c by lambda, so this can be written as function of lambda and t as well. You just need to use the basic substitution given here. Okay, and this in lambda would be nothing but this. So when you use this, you get this value. Okay, so now let us move forward. So furthermore, the intensity of the radiation of the cavity hole is proportional to this. Now this is the energy density. This is the energy density. Okay. So although the exact relation is nothing but intensity as a function of lambda and t, okay, and it is C by 4 and the energy density. Now let us try to have some more explanation that what is its main failure. The one thing is that it failed at explaining the energy curve of the real black body. Real black body means black body approximation. But when you try to find, okay, the total energy, when you try to find the total energy in the frequency range from 0 to infinity, okay, in the frequency range 0 to infinity, you will find that it is going to be infinite because of this frequency square d nu. Okay, so this will lead to infinity in the range from 0 to infinite. So you know that energy density cannot be infinite. Okay, it should not be infinite. Okay, so in any range of frequency there cannot be infinite energy. This issue was well known as ultraviolet catastrophe, and it is PYQ as well. Now the question is, what is the meaning of ultraviolet catastrophe? So catastrophe means some kind of disaster, some kind of disaster. Then why ultraviolet? Then why ultraviolet? Let me explain it clearly to you. Mm, So this is lambda. This is intensity as a function of lambda, and the real curve goes like this. The real curve goes like this, where here you have the maximum value, value of lambda for which intensity is maximum. Okay, so now think that that this is the real curve, and why we are calling it ultraviolet catastrophe, because this was good till this area, okay, in the longer wavelength, but as wavelength reduces it provides the wrong result in this. Okay, so real result should be like this, but this was not the case and this was the case. So they try to know, okay, in which wavelength region did it occur. So this region was actually the wavelength region of ultraviolet. So they called it ultraviolet catastrophe because it happened in this region. Okay, so that is how the nomenclature arrived. So let us try to some of the fundamental flaw of the Rayleigh-Jeans law. So fundamental flaw of Rayleigh-Jeans law is that energy goes to infinite, which is also known as ultraviolet catastrophe, because in that region it has been observed. As this law was derived using the concepts from the classical mechanics, so its failures leads to conclusion that study or development of classical mechanics is not complete as of now. Okay, so we need to do something more, and this is the curve you need to remember always. Next we know that, okay, Wien's law also failed. Wien's law failed where longer wavelength, for longer wavelength Wien's law failed, and Rayleigh-Jeans law failed where at shorter wavelength, at shorter wavelength. So to address this problem there was one final theory which was by Planck, and we call it Planck's radiation law. We call it Planck's radiation law. To solve the underlying issue of the explanation of the X spectrum observed by a black body, Planck assumed that he understood that, okay, the you what Planck called, okay, there are the collection of large number of charged particles and they are performing simple harmonic oscillation. This is fine, but there is one vital difference, that they don't have the continuous energy, they do have the discrete energy, the first kind of concept. Okay, and it was actually year 1900, so people were surprised because of this. Okay, he told that material oscillator within the walls of the cavity can only have the discrete energy. Okay, and we will know what is discrete energy. Okay, just rather than the continuous energy. Okay, so if a particle is oscillating with frequency nu, then energy can have values which are integral multiple of h nu. This is what we call discrete energy. Why we call it discrete energy? Let me tell you. So we know that integral multiple of h nu means you can multiply 1, 2, 3, 4, and 5 and so on to h nu. So it could be h nu, then 2 h nu, then 3 h nu, 4 h nu, and so on. Okay, but if I tell you, okay, these are the energy levels. Okay, so if you ask me, okay, there could there be energy level where we get 2.5 h nu? The answer is no, because 2.5 is not integer. It is not integer. And as per the Planck's hypothesis, the energy must be the integral multiple. It must be discrete, not continuous. Continuous means energy could be h nu, 1 h nu, 1.1, 1.2, 1.3, all the possible numbers in between 1 and 2 would be the energy. But in discrete, where we have the integral relationship, only h nu, 2 h nu, 3 h nu, and so on could be the energy levels. So this is what we are calling quantization of energy. This is what we are calling quantization of energy, where energy is multiple of integer, that is 0, 1, 2, 3 times h nu. And h is nothing but Planck's constant, nu is nothing but frequency. Okay. So know that as energies are now integral multiple of h nu, that is, it is not continuous. So earlier what we have assumed that average energy is kT. Average energy of a oscillator is kT. But now energy has changed, so average energy must change as well. Earlier energy was continuous, now energy is not continuous. So see how beautiful argument it is. Okay, we are just using the common sense. Okay, the energy has changed, so the average energy has to change as well. Okay, so it cannot be kT. It cannot be kT. It has to be something else. Okay, so let us try to calculate average energy considering the quantization of energy. Okay, calculation of average energy considering the quantization of energy. So at first you will have to consider all particles are oscillating with frequency nu. Okay, and at absolute zero, when temperature is 0 Kelvin, all the oscillators will be in the ground state. Okay, so you know that in the classical physics there could be energy zero, but in quantum physics there has the limitation that even at the absolute zero temperature there is some temperature there, some energy there. Okay, so at absolute zero they are in the ground state, and obviously ground state have their own energy. Okay, for example, linear harmonic oscillator do have the ground state energy as h bar omega by 2 and so on. Okay, so you will know it in due course of this particular quantum mechanics lectures. But as the temperature rises, in second case, at the rising temperature, some of the oscillators will jump to the excited state or higher energy levels. So you know this is what going to happen. Suppose there are two energy levels of atoms, like one is h nu, other is 2h nu, and so on. Suppose this is the exemplar case. So whenever you provide the energy, they will take the energy and they will go up. Okay. So this is jumping of the energy level. This is how atoms move, like electrons jump and the overall energy of the atom increases. So we can use the Maxwell-Boltzmann statistics here. We can use the Maxwell-Boltzmann statistics here, and we can write that at temperature T in the equilibrium, the number of, like, temperature has to be maintained. Temperature cannot increase. So number of oscillators with any energy En, we are calling it E1, E2. Like right now I have called it h nu and 2h nu, but now call it E1, E2, and so on. So the nth one would be En. So the number of oscillators with energy En will be n equals to n naught times exponential minus En by kT, and k is nothing but Boltzmann constant. You know it well. Okay, and this is the result which you need to quote by quoting the Maxwell Boltzmann statistics. You need not to derive it. Okay, you just need to quote the all the crude and fundamental concepts, because in physics we can we can segregate the mathematics and physical argument differently. Specifically, in this quantum mechanics, we are not going to delve into detail. That is the case for the thermal and statistical physics. So we know that as per that equation, we can see that as n is going to increase, this capital N is going to decrease. N is like energy level. Level as level is going to tends to infinity, N is going to get reduced, because you know that this N is nothing but N naught and negative exponential. Okay, so we know that higher energy states are less likely to be populated. Okay, and this way you can define that there is average energy per unit oscillator given by this expression, where in numerator you multiply the total number at that particular state of n times the energy itself from n0 to n equals to infinity. N is obviously a small n is number and capital N is a number at that particular state. Okay, n is energy level. Okay, first, second, third, and so on. First, second, third, dot dot dot, nth. Okay, and this capital N is number of oscillators, with energy En. Okay, at that particular level. So, and in denominator, you are going to write the sum of all such numbers. So when you solve it all, you will get finally, because you know the need to have the final result only. And let me tell you, this is a small calculation only. Check here that we are defining it like this, that average energy per unit oscillator will be given by this expression, which I just told you. Just expand it, you solve it, and you will get this expression. So that is why we have minimized this one. Okay, this is not required here, because our chief goal is to understand the wave particle duality. Okay, so now what you have the different. Earlier we have the average energy equal to kT. Why kT? Because we had continuous energy form. Continuous energy form. Now you have discrete energy form. Discrete energy form led by the energy equation equals to nh nu. So you cannot have the same average energy. The average energy now will be h nu by exponential h nu by kT minus 1. Okay, so this is the average energy now. So now you have number of oscillators in a unit volume. Okay, you have number of oscillators in a unit volume given by the Jeans number, which is 8 pi nu square upon c cube, then multiplied by the average energy. This is what we need to do in order to find the energy density. So energy density is number of oscillators in a unit volume multiplied by the average energy. So when you do that, we get this result, which is Planck's radiation law. And you see that there is some exponential curve here, so it is going to fit the curve exactly as we saw in beginning. So it is going to fit this blue line exactly. Okay, and in this way we can also rewrite in the form of wavelength, because we know that frequency is equal to c upon lambda. Okay, so we rewrote it in this form. Okay, and we know that if you if you use that lambda is tending to 0, it will become Wien's law. Okay, it will become Wien's law, and when lambda is tending to infinity, it will become Rayleigh-Jean's law. So Rayleigh-Jean's law and Wien's law both are the subset of Planck's radiation law. So we have actually understood, okay, the black body radiation is following this particular equation, and this particular equation is derived by assuming that the oscillators cannot have continuous energy, but they can only have the discrete energy, and this is what we call the beginning of quantum mechanics. Okay, because we assumed that energy can be discrete as well. The deviation from the classical physics. In classical physics we cannot have discrete energy, but in quantum mechanics we can have. So let us try to have the summary of section 1. So Wien's law states that intensity is inversely proportional to lambda to the fifth power and directly proportional to some exponential function of t. Okay, and it fails at longer wavelength. Similarly, Rayleigh-Jean's law, it is 8 pi mu square c cube kt. Okay, and it fails at shorter wavelength. And we have the Planck's radiation law, which we just studied. Okay, it correctly fits the observed spectral curve, and it has the special cases where it also becomes the Wien's law and Rayleigh-Jean's law. And this is not k, this is not k, this is lambda. Okay, so this is the complete formulation of the black body radiation which we are required to know for the quantum mechanics. And now we are going to start photoelectric effect. So we know that when electromagnetic magnetic wave of sufficiently high frequency hits the metal surface, the electrons are ejected from that metal surface. This is what we call photoelectric effect. This effect was first discovered by Heinrich Hertz in 1887 itself. So there are few observations made, like minimum frequency required to get the electron ejected, okay, is known as threshold frequency. There is some minimum frequency below which there will be no ejection of electron, and we call it thermal frequency. Then we have kinetic energy, which has a maximum value. Okay, so beyond one limit, there won't be more kinetic energy to electron. And we should know that photoelectric emission, like electrons ejection, is instantaneous process. It happens instantaneously. And there is one other observation where the photoelectric current depends upon intensity and not the frequency. So if you increase the frequency, okay, so the current won't increase as it depends upon the intensity. So when you compare all the observations with classical physics and quantum mechanics, you will know that only the last observation could be explained by the classical physics. The first three observations could only be explained by considering the quantum hypothesis. Okay, and that is what Einstein did. He used the Planck's energy quantization criteria to explain the photoelectric effect, and that time it was a big deal. Okay, so Einstein continued using Planck's quantum hypothesis. Okay, that is energy is discrete and it is not continuous. Energy is discrete and not continuous. He explained the incident radiation acts as a stream of bundles having energy h nu. So incident radiation, that is EM waves, electromagnetic waves, okay, these are nothing but bundles of energy, bundles of energy, and later these bundles are known as photons. Later these bundles are known as photons, the massless particles. So when these photons collide with the electron within the metal, provided that the incident stream has some minimum threshold frequency known as mu naught, okay, the energy is transferred to electron and electrons gain kinetic energy, they are ejected. Okay, so the corresponding energy to the threshold frequency is known as work function. So if threshold frequency is mu naught, then work function is h mu naught, which is energy, which is energy. So incident radiation must have this minimum energy to witness photoelectric effect. To witness photoelectric effect. Okay, that is, and this is characteristic of, and this threshold frequency or work function is characteristic of the metal which you are using. So for different metal there will be different wave function. So if you have metal M1, so for metal M1 the work function could be different. That is the minimum required threshold frequency could be different. For metal M2 it would be different, and so on. So if your radiation is h nu, then you must subtract or offset this work function to transfer the energy to electron, which will emerge as Emax, that is maximum value of kinetic energy. That is maximum value of kinetic energy. Okay, so it is very important to notice that this is the characteristic of the metal. Now we have the concept of stopping potential. That is, let me tell you very clearly in this setup that we have one emitter which will emit the electron while it receives the radiation. Okay, and this electron will be collected by collector. There is some circuit where we have used ammeter to measure the current, because if there is flow of electron there will be some current in between both the terminals, and we have here the potential supply here. So what you will do, you will open up this switch in a way that it actually repels the electron, and then you will start increasing the voltage. So we all know that work performed by the charge while interacting with voltage V will be given by work is equal to QV, and this work will actually be in the form of energy. Okay, because we all know work and energy, they both are equivalent. Okay, like you cannot energy is simply the maximum amount of work you can do. So in that capacity, this work at one point will be equal to maximum value of kinetic energy. Okay, and if at that point of time when they are equated, so this electron will actually stop moving to the right. Okay, it will become a standstill at that point of the space, and we call that potential as stopping potential. We call that potential as stopping potential. Okay, so this is what we have written. If the collector plate is made negative, then the photoelectrons will be repelled because they are of negative polarity. And if the potential such applied is greater than the corresponding energy, because we know that this potential will equivalently convert to energy by using this expression Q times V. Okay, so the photoelectric flow would stop. You can notice it from the ammeter used in the circuit, and that potential we are calling it a stopping potential. This stopping potential is very important. Let us see how. So suppose we have a stopping potential, okay, equals to here I need to use one more line because this is not equal to. So in we have this case where the electron flow has stopped, and we are calling it E times V naught equals to E max. So this E is nothing but electron, which is charge, and this V naught is nothing but potential applied. So we know that this is nothing but W is equal to Q times V. Okay, and this is equal to the maximum value of the kinetic energy. So we are when solving it, so it is E times V naught equals to H nu minus work function is nu naught, and this is V. Okay, we know that this is V for potential, and that is mu for frequency. This is potential, this is frequency. So when you equate it and you do some LHS and RHS transformation, then you will get that a stopping potential V naught is equal to H by E, and within bracket mu minus mu naught. So this mu is the frequency of incident radiation, frequency of incident radiation, and this mu naught is threshold frequency, which is characteristic of the metal we are using. Okay, so this is a straight line where you can draw it like this. Okay, and on the practical ground, from this straight line equation you know that what is the stopping potential, because you have the setup like that. You know the threshold frequency, you know the frequency of the incident radiation, you know the value of the electron. So using this you can actually find the value of Planck's constant experimentally. So that is why this is very important, and this is what earned Millikan a Nobel Prize. Okay, so thus the theory as explained established the correctness of the quantum concept, because it was also verified experimentally using the concept of photoelectric effect. At first, it was uh, in the explanation of black body radiation, but now it is in the explanation of photoelectric effect. And now using the slope h by e, which is of course the form of the um, straight line. So Millikan found the value of h practically, and also they both, like Einstein won Nobel Prize in 1921 and Millikan won Nobel Prize in 1923. So he won Nobel Prize for this particular stopping potential case, where he found the value of h, which is equal to 6.626 multiplied by 10 to the power minus 34 joule second for our purpose. So this is what we call photoelectric effect. So it also explained that particle has wave nature. Okay. Now we have the third topic. We have the third topic, which is Compton effect. So this is again important. Why? So it is collision of wave and particle. Why? We are actually going to witness how a photon is going to interact with electron. So we are calling this interaction collision as well. Okay, because every collision is a kind of interaction. So what we have observed, it was observed that when X-rays is scattered using the atom uh, which do have the low atomic weight, for example carbon, then X-ray gets scattered by forming the two intensity peaks. What kind of two intensity peaks? We will just see. Okay, so two intensity peaks were observed. First peak at the incident wavelength and the second peak at the wavelength slightly longer than the incident wavelength. And this whole observation of two peaks cannot be explained classically. Okay, if you try to use the mathematics and concepts of classical physics, then it won't be explained that why we do have two peak, this and this. Okay, this is what it looks like. So let me show it to you. Look, so this is the original wavelength, and this is what you will see when you will witness the Compton effect. Okay, so at original wavelength there will be the peak of intensity, of course it should be, but slightly more than this original wavelength there will be another peak as well. The difference would be minimal. You should see that it is 0.007 angstrom, and angstrom is itself a small quantity which is equal to 10 to the power minus 10 meter. Okay, the angle of such collision is 45 degree. We will see what angle in the schematic. So we can see that this is what Compton effect says. And if you try to explain the nature of this curve, that why the peaks are at two different wavelengths, then classical physics would fail. Let us see how. Classical physics would fail. Okay. So we have this experimental setup which led to the observation. We have the source of X-ray which is monochromatic, that is it is made of mono means single, chrome means color, made of single color, that is made of that means made of single frequency, made of only one frequency. We have this collimator to guide this beam towards the scattering material. Scattering material nothing but low atomic weight atoms, low atomic weight atoms. Okay, and this is X-ray spectrometer which observes the spectrum emitted by this particular scattering. Okay, so it can be moved down this line or this line, so you can observe these intensities at different angle. Okay, so let us see how the classical physics failed to explain the Compton effect. As per the classical physics, an incoming electromagnetic waves drives electron into SHM. So whenever you try to interact the incoming electromagnetic waves, okay, so it will do? It will transfer its energy to electron, and electron will move up in the energy level. Then it comes back and again moves up because energy is still incoming, and in that way it will start SHM. It will start SHM. So this would what happened at the classical level, just like we studied in the black body model as well. And the electron then re-radiates because if you raise the energy level from E1 to E2, then it will come back because they want stability. So while it will go up, it will absorb. While it will go up, it will absorb, and while it will come down, it will emit. So whatever it will absorb from the incoming radiation, the same thing it will re-emit. And this re-radiation, re-emission is known as scattering. Okay, so it will re-emit that electromagnetic wave, X-ray in our case, because that is how we have defined our setup. Okay, and obviously if there has to be equilibrium, then it has to be on the same frequency, okay, as the incident wave. But we know that there are two peaks, two intensity peak at two different wavelengths, so that is not the same frequency. This is failing in the real observation what we have seen just here. You see, this is lambda naught, so this would be corresponding frequency mu naught, this would be corresponding frequency mu. So why we have two different frequencies peaks? It should not be like that. Okay, so this is why the classical physics is actually failing. Okay, so let us try to understand it in little bit depth as well. So let us try to understand this phenomena on the basis of classical electromagnetic theory. The X-ray beam on entering the scattering material interacts with the atomic electrons. Obviously they will interact, the matter and wave always do interact, and the outer electrons can be considered essentially free because they do have the less binding with the atom. Okay, the reason is they are bound with the atom with an energy which is much smaller than the energy of the X-ray beam. The electric field associated with the X-rays exerts a force on these electrons and makes them oscillate simple, simple harmonically with the frequency of the X-ray. Okay, the energy of transfer takes place, and that results in oscillation. The electrons being accelerated will emit the electromagnetic radiation because they have gained some energy. Okay, so they has to come back to their ground state or the less energy state, that is more stable. So the initial frequency of this radiation will be equal to that of the incident X-ray. This is what it has to be classically. Also, you can see that the X-ray beam also imparts some momentum to the electron, which then recoils in the direction of the propagation of the beam. Because you know, if there is interaction, then there will be exchange of force, and whenever there is exchange of force, and mm, there is difference, so it will lead to the change in momentum. So there will be some change in momentum for the electron, that is electron will gain some momentum. And because if there is momentum, so there is will be, you know, a kind of collision, and there will be some kind of recoil as well. Okay, so this is how it goes like. So energy and momentum are carried continuously by the wave, that is electron absorb and re-emit the X-rays with the no net change in wavelength. Okay, it should have been the classically, but in real it was observed that the scattered X-rays had slightly longer wavelength too. If the wavelength is longer, then frequency is shorter, because we know that there is inverse relationship. Using discrete energy packet to explain the Compton effect. So let us see that how discrete energy packet will again save us. So discrete energy packet is the cornerstone which has helped us in explaining black body radiation, which has helped us in explaining photo electric effect, and now it will also help us in explaining the Compton effect. Okay, so Compton used the quantum theory. He assumed that X-rays are a stream of photons with energy h nu, same as Einstein. Okay, the photons from X-ray are making elastic collision with electron within the atom. If it is making elastic collision, then there is no change in the kinetic energy of the system before and after the collision. The kinetic energy is constant. So you know that in every kind of collision, where the system is isolated, you can always apply law of conservation of energy and law of conservation of momentum. So now let us try to do it in the class 12th, where now we have all the simplifications. Now we only need to solve these two equations and we get the answer why there are two different peaks. Okay, and we know that the energy is h nu. Let me tell you, this is the cornerstone. This is the cornerstone of explanation here, because we have assumed the quantum nature. We know that energy is not continuous, but it is in the form of quanta, which is h nu. Okay, so look here, we have the electron, and what happened that the X-rays are sent like this, and X-ray got scattered in this area region, and it got scattered in this. Okay, so electron also scattered, X-ray also scattered, and they cause two different peaks at certain distance. Let us see why in the mathematical formulation. So we will have to define initial and final condition. So we know that energy and momentum of the incident photon is going to be h nu and h nu by c. Obviously, if you are defining that, okay, your X-ray would have the frequency nu, then energy would be h nu for the photon, and you divide then energy with velocity to get the momentum. Okay, so this is momentum of the photon, and this is energy of the photon. Great. And now the photon will get scattered, so its frequency will change. So frequency changes from mu to mu naught. Okay, this is the after collision energy, and this is the after collision momentum. For the electron, what we can say that energy, its rest mass energy is m naught c square. It is approximately 511 kilo electron volt. You should remember this, memorize this as of now. And as it is on the rest, so this is the momentum, which is 0. Now we are doing a very simple task. You are just defining the scenario. Okay, electron is in the rest state, so momentum has to be 0. Electron's energy has to be the rest mass energy, and energy and momentum of the electron after collision will be, because we are in the microscopic realm, so better we use the relativistic effect. So relativistically, we know that energy is given by p square c square plus m naught c square whole square, and momentum, let us call it just p. So now we have initial and final condition. Initial and final condition well defined. We have energy and momentum before, we have energy and momentum after for the photon, and same before and after condition for the electron as well. Now what you will do, you have two simple things. You need to apply law of conservation of energy. You need to apply the law of conservation of momentum. You will get some equations, you solve them, simplify them, you will get something very interesting. So we know that the system is isolated, so initial energy of the system is going to be final energy of the system. So initial energy is h nu plus m naught square, and final is for the photon h mu naught, and this is the energy for the electron. So great. Now we will apply the initial momentum of the system in y direction and in the x direction. So we know that we need to break the direction as well. Okay. Initially, you know that if this is running in this way, so there will be some momentum for photon in x direction, some momentum for photon in y direction. Okay, this is for photon, this is for photon. Similarly, there will be some momentum for electron in x direction and some momentum for electron in y direction. Of course, exactly negative y direction, but we will see that mathematically. So in that you can write that in the y direction, okay, system's momentum, initially there is no motion in y, so it is going to be 0 and 0, but after the collision it has to be h mu naught by c sine theta and minus p sine phi. Okay, so let me tell you that how we have defined angles. So the scattering angle for the photon is going to be theta, the scattering angle for the electron is going to be psi. Okay, so now you can have the sense that why we have sine theta here, why we have this here. Similarly, the initial and final momentum in the x-axis would be for the electron it is, because electron, sorry, for the photon it is h nu by c because photon is in the motion, but electron it is 0. And after the collision the photon will gain the momentum in x direction, which is the cos theta component, and it is p cos phi component. Now we have three equations. When you solve these three equations you will get something very interesting, which you can interpret in that way, which we have the observation those for those two peaks. So now you can simplify, you can see that okay, we have here cos phi, we have here sin phi, so we can square them and add them up, so there will be sin square phi plus cos square phi, so some kind of simplification you will get. So when you square 2 and 3 and then add them, you get that p square cos square psi plus p square sin square psi, and the same similar term in the right hand side as well. So this will simplify to p square, because in bracket you will get cos square phi plus sin square phi, and that would be 1. So you just got p square. And in right hand side you get h square by c square. You are simplifying it, and simplification has just only two steps. Simplification has just two steps here. You just square. This is step one. You just bring like terms together. Bring bring like terms together. Okay. So in that way we can see that okay, we have this h square c square here, and then within the bracket we have the term involving the frequency and the term involving the scattering angle and recoil angle, because electron is also getting recoiled, so we have this theta as recoil angle. Now we can bring this h square by c square to the left hand side as mm, like I think this is c square upon h square, so we can have p square c square upon h square. And now we can do some more simplification, because we have this p square c square term in equation 1 you see here. So what we will do, we will use that p square c square term here, we will use to simplify it, and we will get some better simplification. So when you simplify it, okay, you will get that 2 m naught c square by h is within the bracket mu minus mu naught is going to give you 2 mu naught 1 minus cos theta. And um, you can keep it here, and you can bring these all in the right hand side. Okay, so we'll get this, and this has to be brought here and it has to be solved, so you will get 1 by mu naught minus 1 by mu, and this could be lambda naught minus lambda. So there is change in wavelength here, the term which is given by the term h upon m naught c 1 minus cos theta, and it is defined exclusively as the function of recoil, sorry, scattering angle, because we have defined this theta as a scattering angle. and this psi is recoil angle. Great. So see how easy it is. You just are following the application of law of conservation of energy and law of conservation of momentum. Okay, it is not complex. You are just trying to simplify it as you were doing in the class 10th from the trigonometry chapter itself. So have the confidence, and when you simplify it, you get this finally, where we have change in momentum, change in wavelength, which is equal to lambda c multiplied by 1 minus cos theta. And this lambda c is obviously the constant. It depends on the value of the Planck's constant, mass of the electron, and value c. So you can calculate the value of the lambda c, which is 0.0242 angstrom. Now similarly, you can also find the, and we call it Compton wavelength, lambda c, and this formula is important for you to memorize, because this explains that why there is change in wavelength. Okay, what kind of change in wavelength? See this change in wavelength. Okay, this change in wavelength. So this is defined by that it is Compton wavelength times 1 minus cos theta. So you see how when we used energy of photon as h nu, so we got this value which explains the practical observation. So this is why we can say, okay, the quantum hypothesis was correct, because it is explaining, quantum hypothesis is theory, but it is also explaining the observations, experiments. That is why we conclude that this is not the hypothesis, this is the fact, this is the concept which gets activated as soon as you proceed in the quantum state, quantum realm. Now you can also use the conservation of momentum, which you have two these expressions. So you know that you have one expression like we can equate Pc upon h cos psi equals to mu minus mu naught cos psi. Okay, just by using the conservation of momentum. Okay, and we have already done it here. This all thing. So we are just using it again and again. So when you use it, you divide the equation 4 by equation 5. You simply get cos psi is equal to 1 plus this alpha multiplied by tan theta by 2. This alpha is nothing but h nu divided by m naught c square. This is energy divided by energy, so it is a constant. Now we can also find the kinetic energy of the recoil electron. So how will the electron get energy? Obviously it will get from the photon. So let us try to calculate the difference of energy in the photon before the collision and after the collision. In that way, you will find the energy which is equal to energy of the electron. So energy of incident photon minus energy of scattered photon h nu minus h nu prime, and you take the h common, and this nu prime would be this, using the equations which we have just performed. Okay, and we will get finally this value. Okay, where we get mu divided by mu naught equals to 1 plus lambda 1 minus cos theta by using the momentum conservation equation. Okay, so whatever the interrelationship you are going to get in this all, the only reason is conservation of energy and conservation of momentum. These are very important concepts. Now in the term of the psi, one can also write, because we know that psi and theta are connected. How they are connected? Using this expression, cot psi equals to 1 plus alpha multiplied by tan theta by 2, and alpha is h nu by m naught c square. So see how beautiful it was. So now till now we have studied the explanation of black body radiation, the explanation of photoelectric effect, the explanation of Compton effect. In black body radiation, we studied Wien's law, Rayleigh Jean's law, and we also studied Planck's radiation law. In photoelectric effect, we studied the Einstein's explanation. In this, we studied the value of the photon for h nu. So in this all, the only one thing was common, that you used the condition that energy is the quanta, it is not continuous, energy is the discrete. and this is what we call a starting point of quantum mechanics. So we are done with this particular topic, where we have just studied the particle nature of wave. Now in the next we are going to study the reverse of this, that is wave nature of particle.